Good evening, dear students. Now I want to teach Chatellier's principle. This is a very important concept, Chatellier's principle and factors which can influence the equilibrium. This concept is very important concept from equilibrium lesson. Okay. So Chatellier's principle definition, it states that a change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. Okay, if you change in any of the factors, means effect of concentration change, effect of pressure change, effect of temperature change, effect of addition of inert gas at constant volume, at constant pressure, and catalyst. So these are the factors. If you change in any factor, so that factor determine the equilibrium condition of a system. Understood? If you apply any one of these factors, then that equilibrium system always moving in opposite direction. Simply it is known as Le-Chatelier's principle, opposing direction. Understood? So now you will easily understand these concepts. So these all factors, please listen carefully. So factors which can influence the equilibrium system. So how many factors are there? Effect of concentration change, concentration change, effect of pressure change, effect of temperature change, effect of temperature change, addition of inert gas at constant volume, addition of inert gas at constant pressure, effect of catalyst, okay. So these six are important factors. Understood? So now first one, effect of effect of effect of concentration change, effect of concentration change. Understood? Effect of concentration change. Remember only one sentence that is very important. Always equilibrium reaction shifted from higher concentration to lower concentration. Remember only one sentence, that is important, that is enough. So always equilibrium reaction shifted from higher concentration to lower concentration. Okay, always equilibrium reaction shifting from higher concentration to lower concentration. Higher concentration to lower concentration. Very important. Always equilibrium reaction shifting from higher concentration to lower concentration. Understood? So remember one thing. Here pure solids, pure liquids unaffected. To the system, for example, for a equilibrium system in which, for example, solid term is there in this reaction. Solid term is there or liquid term is there. If we add few amount of solid, few amount of liquid, pure liquid, then there is no change in equilibrium. So aqueous terms, gaseous terms, they are for that system. If we add, then change is there. So please consider this one, very very important. Okay. So example, A gas plus B gas giving rise to C gas plus D gas. This is one equilibrium system, equilibrium reaction. Suppose if we add either A or B, means reactant. Okay, if we add either A or B, then what happen? Reactants concentration increases. Reactants concentration increases. Reactants concentration increases means comparatively products concentration low. Then always equilibrium reaction shifted from higher concentration to lower concentration. Then what happen? Then equilibrium reaction shifted in forward direction. Okay, so very very important statement it is. If we add either A or B, then reactants concentration increases. So comparatively products concentration are in low, then higher to lower means forward direction. Suppose if we add either C or D, then products concentration increases. So products concentration increases means comparatively reactants lower in concentration. Then higher to lower means backward reaction takes place. Which reaction takes place? Backward reaction takes place. Okay, backward reaction takes place. Understood? So simple statements these are. Suppose for example, if you decrease the either concentration A or B, then reactants concentration decreases. Products comparatively high. Then higher to lower means backward direction. For example, if you decrease either concentration C or D, then products concentration decreases. Comparatively reactants higher in concentration. Then higher to lower means forward direction. Understood? So very simple concept it is. Clear? Another example. Fe3 plus aqueous plus SCN minus aqueous giving rise to FeSCN whole 2 plus aqueous. You know, this is yellow color, this is colorless, this is red color. Now this is one equilibrium system. Understood? This is one equilibrium system. Okay, equilibrium system. So to this system, we are adding either small amount of, okay, either small amount of Fe3 plus or SCN. Suppose for example, if you are adding small amount of Fe3 plus, so before the system is in equilibrium initially, then color of the equilibrium system, it is maybe reddish yellow color, means the solution appeared as red color and yellow color mixing. So some yellow red color or red yellow color, partially red color, partially yellow color, we can observe that like solution. But to this system you are adding small amount of Fe3 plus. Then if you add small amount of Fe3 plus, then reactant concentration increases. So obviously reactants concentration increases. Reactants concentration increases means comparatively products concentration low. So higher to lower means forward reaction takes place. Forward reaction takes place means, so this solution, its color will turn into more intense red color. Okay, so solution will turn into pure red color, more intense red color means forward direction. You can experience this reaction in the laboratory very well. Understood? Suppose, for example, if you add small amount of FeSN whole 2 plus, if you add this substance small amount to the equilibrium system, then what happened? Products concentration increases. Comparatively reactants lower in concentration. Higher to lower means backward direction takes place, means finally this solution will become more intense yellow color, more intense yellow color. Understood or not? So by observe the color of solution, we can easily identify whether it is forward direction or backward direction. Understood? So this is very important example, best example. Clear? Now moving to next one, that is effect of pressure change. Effect of pressure change. Effect of pressure change. Understood? Effect of pressure change. Here one statement that is very important. At high pressure, equilibrium reaction shifting, equilibrium reaction shifting, equilibrium reaction shifting, higher number of gaseous moles to lower number of gaseous moles. Higher number of gaseous moles to lower number of gaseous moles. Higher number of gaseous moles to lower number of gaseous moles. At high pressure, equilibrium reaction shifting, higher number of gaseous moles to lower number of gaseous moles. This is at a high pressure. Understood? So higher number of gaseous moles to lower number of gaseous moles. So this is one vessel. So this is one vessel. Okay. So here some amount of gas is there in this vessel. So we we are fixing here one piston. On this piston, if you are applying pressure, then what happen? Gas compression takes place. What happen? Gas compression takes place. Gas compression takes place. So before actually gas occupying more volume, but if you apply more pressure, then volume decreases. Volume decreases means per unit volume area, more number of gaseous particles existed. Per unit volume area, more number of gaseous particles existed at high pressure. Then, according to Le-Chatelier's principle, equilibrium always shifting in opposite direction. Opposite direction means if you apply more pressure on piston, then volume decreases. Volume decreases means all gaseous particles come closer together. Then per unit volume area, more number of gaseous particles existed. Then what happened? Equilibrium moving in opposite direction means equilibrium shifting from higher number of gaseous moles to lower number of gaseous moles. This is completely imaginary process but important. So at a high pressure, equilibrium shifting from higher number of gaseous moles to lower number of gaseous moles because of pressure applicable to gas systems. Understood? Now, example 1. You will understand. Listen. Example 1. 2SO2 gas plus O2 gas giving rise to 2SO3 gas. How many gaseous moles? 3 mole gas. How many gaseous moles? 2 mole gas. So at high pressure, here at high pressure, forward direction or backward direction? At high pressure, higher gaseous moles to lower gaseous moles. Higher to lower means here 3 mole to 2 mole forward. So very very important, this is forward direction at high pressure. At high pressure, equilibrium shifted in which direction? Forward direction. Forward direction. Very very important, forward direction. Understood? Higher gaseous moles to lower gaseous moles. Very simple example. Now, example 2. Example 2. N2O4 gas. N2O4 gas giving rise to 2NO2 gas. 2NO2 gas. How many mole gas? 1 mole gas. How many mole gas? 2 mole gas. Now, at high pressure, higher gaseous moles to lower gaseous moles means higher to lower means which direction? Backward direction. Which direction? Backward direction. Now, at high pressure, higher to lower means backward direction. Backward direction. Now, coming to third example. Hydrogen gas plus Cl2 gas giving rise to 2HCl gas. How many mole gas? 2 mole gas. How many mole gas? 2 mole gas. Now both side gaseous mole same. Both side gaseous mole same. That's why this reaction, this equilibrium reaction unaffected with pressure. Unaffected with pressure. Understood? Because both sides same number of gaseous moles. That's why there is no effect. There is no effect on this particular reaction. Example 3. So clear? I hope everyone understood this one. Now, moving to next factor. What is the next factor? Effect of temperature change. Effect of temperature change. Effect of temperature change. Okay, effect of temperature change. So this is also very important factor. Here also one sentence that is very important. Exothermic reaction. Okay, exothermic reaction. Low temperature. Exothermic reaction. Low temperature. Forward. Forward reaction. Forward reaction. Equilibrium shifting in forward direction. Exothermic low temperature forward. This one sentence is very important. Remaining three cases we can easily write. We can easily write based on this first statement. Remaining three we can easily write. Exothermic high temperature. Exothermic high temperature. That is backward. Backward. Now endothermic. Endothermic low temperature. So endothermic low temperature. Which one? Backward. Backward. Endothermic. Endothermic high temperature forward. So these are very important conditions, but if you remember the first condition, remaining three we can easily write. Exothermic low temperature forward. If you remember this one, remaining three you can easily write. Exothermic high temperature backward. Now low temperature endothermic backward, high temperature endothermic forward. Now here why exothermic low temperature forward? Exothermic reaction means delta H negative. Heat liberated, heat energy liberated. Understood? Exothermic means delta H negative, heat liberated. Endothermic means heat absorption takes place, delta H value positive. Now coming to exothermic reaction. Exothermic reaction, delta H negative, heat liberated. For example, up to particular temperature means for up to particular optimum temperature. For example, if you increasing the temperature up to particular temperature, even though it is exothermic reaction, it is liberating heat energy. Up to particular temperature, it is liberating heat energy, means exothermic reaction only. Exothermic reaction, only exothermic. So when you giving or when you raising temperature up to particular temperature, then it is liberating heat energy. Once if you exceeding that particular temperature, then what happen? It starts to absorption. It starts to absorb the heat energy, means that exothermic reaction will become endothermic reaction. That's why up to particular temperature means up to particular lower temperature, exothermic reaction moving in forward direction only. But once if you exceeding the temperature, that reaction starts to absorb the heat energy. That exothermic reaction will become endothermic reaction. That's why remember, up to particular temperature, lower temperature, exothermic reaction forward direction only. But if you increase the temperature abnormally, then what happen? It will become endothermic, because it will become endothermic, means reaction shifting in backward direction. That's why exothermic low temperature forward, exothermic reaction high temperature backward. So very important, very important. Understood? Yes. One sentence. If you remember, one sentence. Exothermic low temperature forward. Remaining all you can rewrite. Now, next one. Effect of. So what is the fourth one? Addition of inert gas at constant volume. 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 So addition of inert gas at constant volume, there is no effect on equilibrium system. Effect on equilibrium system. Understood? There is no effect on equilibrium system. Why? So this is the vessel. Okay, this is the vessel. Okay, this is the vessel. Here, one equilibrium system is there. To this equilibrium system, we are adding some amount of inert gas. Some amount of inert gas. Understood? Some amount of inert gas. Inert gas means helium, neon, argon, we can add inert gas. Sir, why we are adding only inert gas? Can we add any other gas? If we add any other gas, then which product you are expecting, maybe that product not form. Maybe other product will be formed. Understood? But if you add inert gas means noble gases, helium, neon, argon. When you add inert gas to the equilibrium system, that inert gas only it can affect the equilibrium system, but it is not merging in the reaction. It is not merging in the reaction. It is not reacting. It is not reacting with the system. Understood? So inert gas particles, they are not reactive with the reactant particles. Understood or not? Yes. So if you add some amount of inert gas, for example, before equilibrium system, suppose 100 particles are there, 100 gaseous particles are there. 100 gaseous particles are there. In equilibrium system, 100 gaseous particles are there. To this 100 gaseous particles you are adding, for example, 10 neon particles, inert gas particles, 10 neon particles. 10 neon particles. Then overall particles, how many particles? 110 particles. How many particles? 110 particles. Understood or not? 110 particles. Here volume, constant volume. So number of particles increases now. Then resultant pressure increases or resultant concentration increases. But individual particle pressure, individual particle concentration, that is not changing. So individual particle concentration or pressure not changing. That's why there is no change in equilibrium. Understood or not? There is no change in equilibrium. Why? Here volume is constant. Volume is constant. So if you are adding some amount of inert gas particles, overall particles increases. Overall particles increases means overall pressure increases or overall concentration increases, but individual particle its concentration or pressure not changing. That's why there is no affect the equilibrium system. So very important, there is no effect on equilibrium system when we add inert gas at constant volume. Very important concept. Now moving to next one. Addition of addition of inert gas at constant pressure. Addition of inert gas at constant pressure. Okay, addition of inert gas at constant pressure. Now, here addition of inert gas at constant pressure. Here equilibrium reaction shifting from lower gaseous moles to higher gaseous moles. Lower gaseous moles to higher gaseous moles, equilibrium reaction shifting. Okay, equilibrium reaction shifting from lower gaseous moles to higher gaseous moles when we add inert gas at constant pressure. Here equilibrium system moving from lower gaseous moles to higher gaseous moles. Okay, here equilibrium system moving from lower gaseous moles to higher gaseous moles. Lower number of gaseous moles to higher number of gaseous moles. Very important. What is the reason? What is the reason? When we add some amount of inert gas to equilibrium system at constant pressure, then resulting volume of gas increases. Is it right or not? So 100 gaseous particles are there in a system, equilibrium system. You are adding 10 neon particles. Then overall particles, how many particles? 110 particles. Number of particles increasing. But here volume is not constant, but pressure we are maintaining some constant pressure. Here volume is not fixed. So that's why number of gaseous moles increases now. That's why volume of the gas increases. Number of gaseous moles increases means volume of the gas increases. So if volume of the gas increases means per unit volume area existing gaseous particles decreases. Existing gaseous particles decreases. Then what happen? Always equilibrium reaction shifting in opposite direction means equilibrium reaction shifting from lower gaseous moles to higher gaseous moles. So that is the concept. Understood? So now write down here, when we add some amount of inert gas to the equilibrium system at constant pressure resulting volume of gas increases. Resulting volume of gas increases. Volume of gas increases. Therefore per unit volume area, per unit volume area, okay, per unit volume area, number of gaseous particles, number of gaseous particles decreases. Therefore, therefore, equilibrium shifting, from lower gaseous moles to higher gaseous moles. Okay, so very important concept it is. Lower gaseous moles to higher gaseous moles. When we add some amount of inert gas at constant pressure, lower to higher. Understood? So example N2 gas plus 3H2 gas giving rise to 2NH3 gas. 4 mole gas. Here 2 mole gas. 4 mole gas, 2 mole gas. Addition of inert gas at constant pressure, lower gaseous moles to higher gaseous moles. Lower gaseous moles to higher gaseous moles means here which direction? Backward direction. Equilibrium shifting in backward direction. So now example 2. 2SO3 gas giving rise to 2SO2 gas plus O2 gas. 2 mole gas. Here 3 mole gas. So lower to higher gaseous moles means forward direction. Which direction? Forward direction. Now third one. Carbon solid plus O2 gas giving rise to CO2 gas. Already I told you solid to unaffected, no need to take. So 1 mole gas. Here also 1 mole gas. Understood? When we add some amount of inert gas to equilibrium system at constant pressure, here 1 mole gas now, no effect. So both sides same number of gaseous moles now, no effect. No effect on equilibrium. No effect on equilibrium. No effect on equilibrium. I hope everyone understood this concept. Yes. So now last one. Effect of catalyst. Last one, effect of catalyst. Effect of catalyst. Okay, effect of catalyst. Effect of catalyst, catalyst can increase the rate of reaction by decreasing the activation energy or path length. Okay, what is the catalyst definition? Catalyst can enhance the rate of reaction by decreasing the path length. If path length decreases means activation energy also decreases. Okay, by decreasing the path length or decreasing the activation energy, decreasing the activation energy, activation energy. Okay, decreasing the activation energy. Catalyst can enhance the rate of reaction by decreasing the path length or decreasing the activation energy. That is catalyst. What is the use of catalyst? Catalyst can enhance the rate of reaction by decreasing the activation energy or path length. But catalyst cannot affect the equilibrium system. Why? So very very important. Catalyst can increase the catalyst can increase the rate of rate of forward reaction and and backward reaction equally. Very very important point. Catalyst can increase the rate of forward reaction and backward reaction equally. Okay, forward reaction, backward reaction. It can enhance the rate of forward reaction, backward reaction equally, means again we are getting the state of equilibrium. So presence of catalyst to equilibrium state achieving early, equilibrium state achieved early, but it could not disturb the equilibrium. Remember or not? Suppose absence of catalyst, equilibrium achieving, suppose 30 minutes late. Presence of catalyst, equilibrium achieving 30 minutes fastly. Understood? But finally equilibrium achieving only. So it could not disturb the equilibrium system. So presence of catalyst to equilibrium achieved early. Understood or not? Understood or not? But it could not disturb the equilibrium system. Clear? So presence of catalyst we can achieve equilibrium state early, but but catalyst catalyst cannot affect the state of equilibrium. State of equilibrium. Understood or not? So very very important point. Catalyst cannot affect the equilibrium system or state of equilibrium. Equilibrium system it could not disturb. Understood or not? So very very important concept. It is Le Chatelier's factors, Le Chatelier's principle, factors affecting our equilibrium system. So effect of concentration change, effect of pressure change, temperature change, addition of inert gas at constant volume, at constant pressure, catalyst. Among these all factors, addition of inert gas at constant volume, there is no effect. Addition of inert gas at constant volume, that condition cannot affect the equilibrium system. Addition of inert gas at constant volume. What is the another factor? Catalyst cannot affect the equilibrium. Understood? Two factors cannot affect the equilibrium. So I hope everyone understood this concept. This is very simple concept and important concept for NEET and JEE. Okay, thank you so much.